All right, well, welcome back to another day of dynamics. We're gonna jump in with this here, and oh, there we go. We're gonna start out with some curvilinear motion. This will be our next system, our coordinate system of how we're gonna think through things. And so we'll look at, like I mentioned last time, we'll look at some systems where we set up an XYZ coordinate system and do our derivatives and whatever else to go between position, velocity, acceleration using that coordinate system. And in the subsequent days, we'll do it with coordinate systems that follow the particle, depending on what sort of accelerations and what makes it easier to manage. Um, you're looking at it real funny. It'll make a lot of sense. It actually makes things very, very sleek for certain situations where it makes sense to follow the particle with the coordinate system. But for today, we're going to be doing our typical XY or maybe XYZ if we're in 3D coordinate system. And that's how we're going to describe the motion that's going on. All right, so here we could describe this in an XYZ coordinates, right? We could plot, for example, its position versus time, and then we could use that to take a derivative, find velocity, derivative once more, find acceleration. And the nice thing about it, when we put it on a coordinate system, is we can split that into its X, its Y, and its Z, like we've done so many times before. But you can take the derivative of just the X motion and get just the X velocity, right? And the X acceleration if we go one step further. So we can split it into those three components. And if you wanted to find the magnitude of the velocity, right? Super Pythag, exactly. We just do the square root of the sum of the squares, like we've done with other vectors in the past. And now it'll just be a velocity vector with three components and an acceleration vector with three components. So that lends itself to a whole plethora of different applications, right? But we could use that to find at any instant the velocity, the acceleration, the position, as long as we can come up with some way to relate those to time, like we did on Monday. So here's another application, right? We could come up with some pathway per time and take derivatives in the x, y, and z this time. Yeah. So that's what we mean when we say curvilinear motion. We're just using vectors to describe the motion in 3 dimensions or two. Um, but if we have some path function s and we've got a vector that is its position from the origin, right? I guess that's the vector that's probably the least intuitive. It'd be easy to imagine a velocity vector going in different directions. A position vector would just be a length from the origin to its current position. And so that's what this R is. It's just, okay, what's its position, X, Y, Z, and it could have some magnitude from the origin as a function of time. And so as that as that position vector changes, we've got a delta r, would just be, r prime minus r, so the current position minus the previous position. That's how we could think about coming up with its change in position. And so velocity then would be the change in r over the change in time. Right? Just the change in position over the change in time. But we're making it that r position vector so we can think about it in terms of vectors this time. Right? And so you might want to get the instantaneous velocity and do a dr dt rather than an average velocity, which would be the total change in position over the total change in time. But if we wanted an instantaneous velocity, then we got to do a derivative of that position vector. So here's an important thing to realize anytime we're talking about the velocity vector, it's going in the direction that the thing is going. So if we have the pathway here, this blue line or this blue curve, if that's the pathway, the velocity is always pointing the direction the particle is going. So with that, that means it's always going to be tangent to the curve, right? So at any point on here, the velocity is going to be tangent to that pathway.
They're always tangent to the curve too.
Right, exactly. Yep, yeah. So when we take the derivative of the change of the r vector, the position, that gives us the velocity vector tangent to that path. Good. Okay, so the magnitude of that velocity vector would just be the speed, right? It would just be the number with no direction. And so we could get that as a total. We could break that into X, Y, and Z if we wanted. There's a lot of things we can do with that. You bet. Yep.
Thank you.
Yeah. So it's basically just walking us through thinking how would we get the magnitude of that? It would be the instantaneous speed. Take the derivative, you get a magnitude of that vector. All right. So acceleration, nothing new here. We're doing a derivative one more time, but it's the rate of change in the velocity, just like before, right? Acceleration is the rate of change of the velocity. So if your velocity is always tangent to the path, see how this one on the right here, that's the beginning one, and then here is a fraction of a second later, right? So our velocity changed from up and to the left to slightly more to the left and less up. So that change in its direction and maybe change in the speed as well would be acceleration, right? And the rate at which that happens is what we're interested in. So as we go from that vector to this vector, you notice what they've done here. They just put these both so that they're concentric, right? They're intersecting at that point O now. So we could say the difference between those two vectors is delta V. We could then use that to come up with an acceleration vector would be equal to that change per the amount of time that it took, right? We could get an average acceleration if we did delta V over delta T, or we could get an instantaneous rate of the change of the velocity, which would be the instantaneous acceleration by doing dv dt. Now, what do you notice about the acceleration vector? Is it going to be tangent to the curve of the path?
No, it's like it's perpendicular to it.
Yeah, and it's not exactly perpendicular. It could be. What would it mean if it was parallel to the velocity vector and still tangent to the path?
Wait, sorry, can you explain that again?
Yeah, what would the condition have to be for it to have an acceleration that is tangent to the path in the same exact direction as the velocity?
Going
Speeding up in the line.
Yeah,
Oh,
So
right.
only the magnitude was changing, the
Right.
direction stayed the same.
Exactly. Yeah. So if you're just changing the speed, then your velocity and your acceleration would be in the same direction, tangential to the completely straight path, right? But if it's turning at all, that means you're accelerating in whichever way it's changing the curve to, right? Whichever way it's turning is where the acceleration is going, in addition to acceleration speeding it up or slowing it down, right? So in this case, it looks like it's slightly forward, so it's speeding up a little, and it's inward, so it's turning to the left in this case, right? So we'll see that most of the time it's not going to be tangential unless you're just going in a straight line. If there's any curve at all, it's going to be pointing which direction compared to the curve. Inward or outward.
we're pulling it.
Exactly, yeah. Yep. So the acceleration will always turn it in the direction of the curve, inward to the curve. Good. All right. So, like I'd mentioned, we're going to be able to split this into an X, Y, and Z, and that makes things a lot more manageable in some cases. We can also use maybe the total vector to find only individual components if we know pieces of that, but not all of the components X, Y, and Z. So we could split those into something like this. So we could make a function of time for the X. We make a function there. We can make a Y function of time. We can make a Z function of time. And we could spell those all out as a position vector R here and just have the X, Y, and Z components. Or we can split those out if it's easier, if it's more manageable. We can have an X, Y, and a Z function, which we could take derivatives of to find velocities and accelerations of the individual components. So sometimes that's nicer to deal with them individually rather than the whole position vector all at once. But the position vector then, right, where the particle currently sits position-wise would just be the square root of the x squared plus the y squared plus the z squared, right, our super Pythagorean theorem. And you could get the magnitude of that. And if you take a magnitude and divide it by its own, or if you take a vector and divide it by its own magnitude, what do we end up with? The unit vector, yeah. So if we wanted a unit vector in that direction, that's what they're getting at there at the end. Once we have that in place, we will be ready to find velocities of individual components. So we like to do that as both a vector and split apart, like I mentioned. Oh, good there. Oh,
Alright.
cool. So yeah, once we split that up, we do the dr dt of that position vector. And we end up with an x, y, and z component of the velocity. Another way to write that is just x dot. And the dot always means time derivative. We took a time derivative of the x function of time and came up with x dot, the same as dx dt, right? So we'll use that throughout this whole class. We'll put a dot on things that we take a time derivative of. Just make sure that you're not doing that as anything other than time derivatives only, is what the dot means. So yeah, we can come up with a y dot, dy dt, and a z dot, dz dt. And by the time we come up with those, we've got the magnitude with the super Pythag again. Square root of the sum of the squares of each of those components. Any guesses what we're going to do next? Hey, exactly. And any guesses what we might call the acceleration?
We're gonna have double dots.
Double dots. Exactly. Yep, yeah, we'll have an x double dot would mean we took the time derivative 2 times and got an acceleration.
I feel like we should get permission to call them umlauts instead of double dots. Umlauts have the 2 dots over a letter to like tell you to pronounce it.
In
weird.
different,
A lot of them in
like,
Swedish.
yeah, different languages have the 2 dots. So we've got x umlaut, x double dot.
So
We've, or maybe I should just pronounce the letters differently. Like instead of Y, now it's like E. It's usually changes a vowel or something, right?
Scandinavian way.
A double dot.
And finally, well, you probably saw this one coming too. We know the magnitude of acceleration if we know each of the individual components. We do a Pythagorean theorem. So you can see the elegance of this method. Right? Really kind of what you'd expect to be able to do. And it's not always the easiest way, but it is, if you can come up with an equation, a function that describes your motion in the x, y, and z, then this is a pretty good way to go. Sometimes there's simpler ways to approach problems, and that's why we'll choose a different coordinate system in other chapters. All right, we all good there? Oh yeah, and like we said before, the direction of A is usually not tangential to the path. If you're going on a curve, it would not be. All right, we'll try an example out here.